All right. So when a failure occurs, any number of possible components could be faulty. I talked about that in the beginning. So today there are two predominant approaches. There are trace analysis tools, some of which are listed here. And these are application layer tools for the most part. They don't really work for platform faults that might happen in infrastructure, and they certainly don't work across the network. They don't know about things like my Wi-Fi or my ISP has rate limited something, or there's some firewall rule somebody's put in place and decided that my packets are not going to get through, or certain packets are not going to get through. At the other end, there's a lot of very good research and I think increasing deployment of network telemetry. These are not cross-layer. So these are things that are inside of the network that keep track of nuanced statistics. But one of the hard problems there is trying to figure out how you connect the statistics with what's going on in the application. You might have a packet loss of something, you might have some delays going up, but how do you tie in a user-perceived failure or fault with something that's happening in the network? I think we're missing that level of connectivity. So we need something better. So we first of all want to start with the user, what the user should be doing, rather than these 3065 error codes or the negative 20, I don't know what's the negative error codes, but the negative 27 error code or whatever it is. So we need a better way to do it. So when a component or a user or some piece of software detects that something is amiss, this could be done automatically with some performance metrics that are being tracked by a client or by a user. Something goes wrong. The thing you want is for the user to press a red button, which is called WTF. And it's not what you think it means. It means, where's that fault? And you press the button, and what the system does, and obviously it isn't going to do it, it's not going to start thinking about what to do then. It's going to have collected enough information over the running of the system or application so that in real time, with the ideal being within a sub-second, perhaps a second or two, it traverses this rather complicated graph of application components and middle box components and endpoint software and router software and everything to come back and tell the user something like the fault was likely in component X in domain Y. And at that point, you have far greater information for people to go trawl through terabytes or hundreds of terabytes of log data to try to figure out what's happening. You get much greater visibility by pinpointing the fault. It's a little bit like, you go to the doctor and you say that, I'm not doing well, something or the other. They do a bunch of tests, and then they pinpoint what it is before the detailed diagnosis. So trying to kind of quickly find where a problem might be is really the only goal of this proposal. And what's important here is a mechanism that satisfies three cross purposes: cross-layer, cross-domain, because these applications are spread across many different domains, and cross-application. And the question is, how do you actually do this? Because in any given one of these components today, there is plenty of diagnostic information in practice. There's enormous amounts of log data, lots of which are probably useless for any given problem, but it exists. And it's completely untenable in real time to go in and start trawling through it, not to mention the fact that people are probably not going to want to share all their log data and everything, all the private information. So what can we do? So the proposal has two parts to it. The first part is we're going to view the entire application or system as a large graph of elements. And what's an element? An element is anything that is capable of generating its own error. And it could be as small as a middle box that has a little NAT functionality in it. And we would like to get into these small elements. And elements get connected to each other in a graph at different layers. So an example, if you have a little web component running on some web server somewhere, that would connect to its local networking stuff, whatever the networking libraries that it uses. It may connect to other services that it interacts with, but it would also connect in this graph with the client that's communicating with it. So in the layered structure, any peer interface, any up or down interface, that induces this big graph. And no one really knows what this graph is, except every component might have, every element might have local information. So it just means that the components interact directly with each other. And a lot of this interaction might be asynchronous. And in practice, there's a sort of time limit to how much you view this. So for example, if I make a change in a configuration and 6 days later something fails, well, this proposal might or might not work. But if you make a change somewhere or something happens and within a few seconds or minutes, it has an effect, that could get modeled in this graph. And then each element periodically produces and emits these things called health bits. And what these health bits are is something that depends on the status and health. And no other component really understands how these bits are produced. The element does. And the only rule that we insist upon is that directionally it be accurate. What that means is you have a fixed number of health bits or a small number of health bits, and the all ones bit sequence might mean something like everything is horrible, and the all zeros might mean something like everything is great, and you have a few levels in between. We don't specify, we don't really care about specifying the details of how it's implemented. We're not going to do that. All we care about is that there's a narrow interface. And the thesis is that because when something goes wrong, not everything is breaking at the same time. When there's a problem, there's a way to analyze these bits and uncover its location in a prompt way. So there's three mechanisms. There's a way to compute and emit health bits at each element, which is something that we're working on. Upon initiating that red button, the WTF, there's a way to inspect health bits, and you might proactively have collected them and stored them in various places. And then there's a way to run an inference algorithm to return the most likely fault location over the inspected health bits. So to summarize, there are three key principles in this proposal. The first one is that these health bits are an intentionally narrow interface. No tight specification of how these are computed. They just happen to be directionally correct. These bits could be stored for as long as or as little time as an element decides. And these health bits are propagated not completely widely like in a linked state protocol. The elements themselves or their administrators decide how far to scope or propagate these bits. And as long as these principles are held, our hypothesis is that we can make such a system work, and that's really what we're working on. And I should say the bulk of the work is being carried out by my co-authors. Will and Emily are the kind of the lead students on it. And I'm going to end with a quote here that either came from Scott Schenker or Groucho Marx. Who can tell the difference?
We have time for a quick question.
I was wondering, how would you align incentives for people who want to do this? So specifically, when failures happen, organizations have the incentive to basically claim they're innocent, right? Yeah. Is it my interest for somebody else to be at fault? So why would I want to take this on?
Yeah, I think that I think the way things are going is there's tremendous negative publicity when things go wrong. So I do think it's the same sort of philosophy behind why organizations decide to have some sort of cooperation, exchanging information for something like BGP. But ultimately, it's because your users care. And if it doesn't work, they're going to go to some other competing service. So I think it does incentivize everybody to try to fix problems. And so I think that that's what we're driving.
Let's thank the speaker once more. And our next speaker is Adrian Berrick, professor at ETH in Zurich. He doesn't need an introduction either, but I am going to say that over the last few years, he and his team have done what I thought was impossible, which is to convince ISPs to deploy a new internet architecture. So what he will talk to us about today is a small part, I guess, of this video.
Thank you very much. And I'd like to start off by saying I was supposed to give the talk, but unfortunately had trouble with his plane. And so now you put up with me. But he will be here later today and tomorrow as well to answer questions and mingle with us. All right, so this work was done in collaboration with Brave, Alex and Ahmet and Philip from Brave, together with Matthias, Jordi, and Francois at ETH, and Martin at OFU in Magdeburg. And essentially, I'd like to take you on a journey now for integrating path-aware networking with the Brave browser and tell you about what happens when you try to use path-aware networking in browsers and where to make decisions for paths in the networking stack. So I'll start out with some background. So essentially, the observation is that the browser has become a platform for network innovation. And we've had several technologies, such as QUIC or DNS or TLS, DNS or TCP, VPNs, or etc. Essentially network-based mechanisms that have been implemented directly in the browser. It's quite an exciting development. Next, I'd like to also give you some background on path-aware networking. And we've been working on this SIAM next generation internet architecture for the last 13 years. And I'll give you a very quick overview of how that works. So in essence, this slide shows different isolation domains. So autonomous systems are grouped into these isolation domains. And what the control plane is doing is essentially constructs the path segments and then also disseminates these path segments to end hosts to then fetch them and select how they want to traverse the network. So here's an example of a host in ASF that wants to communicate with a host in ASS. And it obtains these 6 path segments, and it can now combine them into 2 different end-to-end paths. And this information also goes into the packet header with the payload, and so you can select on a per packet basis how you'd like to traverse the network. So given we've been working on this from a security perspective, for the most part, there's a lot of cryptographic aspects that I'm skipping here, but rest assured, every aspect in SIAN is not only efficient, but also secure. But the focus of today's talk essentially is how can we make decisions for these path segments. Because what's really exciting is that you can add additional information about the paths, and then the end host actually has a lot more information to select these paths. In fact, you can add latency information, and before you even send a packet, you can then obtain some indication about what latency you can expect on this given path. And of course, you could say, well, I can just probe, but actually in SIAN, we see that we have, in some cases, 20 plus path segments you can combine. So ending up with hundreds of different paths you can obtain. And so it will not be practical to trying to probe all the paths to get this information, because you literally have hundreds, potentially hundreds of different combinations. So not only latency you can add, but also loss and expected loss, or NTU, of course, is already added, expected bandwidth, and so on. And these are very discrete quantifiable properties that an operating system-based implementation could make use of, for instance. And then there's also additional properties that are more qualitative, more subjective, that are more based on the user to decide what type of paths or what kinds of properties it actually would like to obtain. So these properties include geofencing, essentially avoiding some parts or some autonomous systems. We're also ensuring that your traffic stays inside an isolation domain. We're also ESG type properties, such as screen routing, and perform routing based on carbon footprints, or also the price and so on. So you can imagine a lot of different types of path properties that are really very much dependent on the user, what preferences the user has. So now to the first time talk, there will be another one tomorrow. The question is, how closely do you want to integrate these decisions with the browser itself? So should the operating system perform these selections, or should these things happen directly in the browser? And in essence, one of the points is that some of these properties, the operating system itself cannot really make a decision, because it really depends very much on user-based properties. So an interesting research question is, how do you put all these things together? And where do you make decisions? It could also happen partially in the network, or also in middle boxes, and so on and so forth. So now looking at this integration of SIAN and the Brave browser, we made a prototype implementation where we built an extension that essentially makes use of a HTTP proxy that then can use both IP and SIAN as well. And essentially the user can now configure path policies and see also network statistics to change these path policies, and the system can then both use SIAN and IP. And so in essence, the local host then has this proxy, and if the local host is in the SIAN-enabled network, the system automatically, based on François' client bootstrapping, automatically picks up all the SIAN configuration parameters and can then use this local network. And if the remote web server is also in a SIAN-enabled network, and it also runs a reverse proxy that we wrote, you can now benefit from all these properties and going directly from the host all the way to the server. And so the user experience is very simple. The user essentially installs a browser extension and can now see which parts of the website have been downloaded over SIAN and which parts have been downloaded over traditional IP. What's really exciting is there's no operating system upgrade required. So the entire sign aspects are purely implemented directly in the application. And so you can imagine simply updating your web browser, then having direct support for a next generation internet architecture. So I think this is actually quite an exciting side aspect of this paper, the fact how easy this can be on the end host. So here we see a quick demo. And again, please see François tomorrow for a more extensive demo to actually see this. Since it's seamless for the user, this website was not downloaded over SAN, the main part of the website, but other components were in networks that are not SAN enabled, and so they were shown in red. But in essence, it's very fast, and even though this is just an initial prototype implementation, it's quite usable. So here you can already set a property to say, I like my traffic to stay inside these isolation domains, and you can also enforce this to make sure the traffic cannot leave the isolation domain. And if you set a strict policy, if the web server is not SAN enabled or is outside that isolation domain, it essentially will fail fetching that image. So there's, of course, a number of challenges if you build this. The first challenge is partial availability. Of course, the number of domains that deploying SAN is not that large so far. We hope it keeps expanding as it currently is. There are 12 ISPs already offering SAN service, and more it's spreading now, but of course it's by far not deployed in most destinations, and so that's of course the first challenge. And so we have an opportunistic mode by default that uses SAN if it's available and can then benefit from these path optimization properties. Also, for server-side adoption is an issue, and so for this we distribute a reverse proxy solution that is seamless and interoperates with your web server to avoid having to upgrade the web server. The demo that you've seen essentially uses ETH has a Microsoft web server, and it works seamlessly with that whole infrastructure. So the evaluation showed that the system adds a little bit of additional latency because it's a prototype implementation using this proxy. But actually, in some cases, we were able to also, we noticed speed ups because the SAN internet was able to offer lower latencies than today's internet, and due to the different paths that were available, so we actually did observe some faster downloads thanks to that. So, of course, there's a lot of opportunities if you think about this. The browser is a really exciting platform for innovation and adopting such new protocols. And so the rapid update cycle and also enables rapid distribution of new networking technologies. So users can also make use of these new properties to now express different types of preferences, path preferences they would like to use, without exposing them to remote third parties. So it's all purely locally applied, and decisions are being locally made. And so there's some, of course, privacy benefits without using a third party for obtaining these kind of advantages. One really exciting direction we're looking into is CO2 reduction through green routing, and essentially selecting paths also based on the carbon footprint of the path. If you are excited or if you have doubts, come talk to me about this. There's quite some surprising aspects in these things. Some of the risks include fragmentation across browsers, implement this technology, trying to discriminate users based on the network policies they prefer, or also simply by having additional mechanisms in the stack. So there's an additional opportunity for potential malware. But one example also is Brave includes Tor, and so SAN is a much smaller component than the Tor systems. So in future work, there's a number of exciting research you can do. So for instance, you can do a path negotiation between the server and the client, and the server essentially sees which path the client comes in and can then through a negotiation, direct the client to connect over a different path, including using secret or hidden paths that are not publicly knowable. So after authenticating the user, the server can migrate the connection over a pristine or we call it hidden path that other users may not see actually. So, or you can also work on the versatility of policy language, how to make use of all these new properties and how to expose them to the user. It's another interesting challenge. And crowdsourcing and also automatically changing the policies based on what the user is doing. So there are lots of opportunities. We're also now expanding the global sign network and provide connectivity also to education and research networks. There's a URL here. And you can contact me if you're interested in this. So this is really the global sign production network, which is really not an overlay. So that's important. It's really a native, what we call BGP-free network, not relying on BGP for any of the global communication. So that's quite exciting to obtain next generation internet access without needing to rely on today's internet. Essentially, sign operates side by side with today's internet. So it's quite non-invasive. It's quite easy to use at the university. Essentially, all it takes is setting up a border router, which is essentially can run on a VM. And so it can be quite simple, and then the whole university can benefit from this service without any additional equipment. And so thanks for your attention, and if you have questions, please check with François.
Time for one quick question.
Hi, this is Arjun Hammer from NYU. So I was sort of curious, how users come up with these policies? Like, that being predicated on the fact that end users want to specify path policies. How do even I, as a fairly intelligent end user, come up with a path policy that meets, for example, an ESG goal?
So the simplest one would be, for instance, a CO2 policy. And there, I imagine it has to be very simple, like a slider. So you say, how important is latency and bandwidth to you, as opposed to conserving and saving some amount of CO2. That would be a very simple policy the user could set. If the user doesn't want to set anything, I guess the default will be the highest performance, the highest performing path. But some users could then say, well, I do care about carbon footprint, so let me.
Where does the metadata come from? Where does carbon footprint come from?
So we're starting to add this to the path information already now. Right now, the precision of these parameters is not that high yet, but we want to essentially start the ecosystem that this information is there. Then in the second step, through a certification process, enable an entity to provide certified CO2 information to ISPs, and then add this, and this will be periodically validated.
Let's thank once more the speaker. Our next speaker is Gina Yuan. So she's a fourth year PhD student at Stanford. So she's co-advised by David Mazieris and Matej Zacharia, but she's also working with wonderful professors like Keith Winstein. And she's broadly interested in networking and security. And today she will introduce to us the QUAC, right? Which is this beautiful new construct that makes it possible for in-network proxies to work with encrypted transport protocols.
Hi, thank you, Katarina. I'm Gina. Today I'll be talking about sidecar protocols and paranoid transfer protocols. So let me start with a story about TCP/IP. When TCP/IP was first invented, IP was spoken by every hop along a network path, while TCP was only spoken by hosts. So routers would use IP to help data find its way to its destination, while hosts would use TCP to ensure the reliability of its delivery. But in practice, the right way to implement TCP depends on the particulars of the network path. On the left, we have a high delay satellite link connecting the router to the moon. On the right, we have a shorter but lossier link, such as a cellular network or Wi-Fi. If the host on the right sends a packet to the moon, it could take a long time for it to receive this acknowledgement because of the high delay link, and then that acknowledgement could even be dropped. But what if the routers knew about TCP? By the 1990s, middle boxes started using TCP to try to improve the quality of the underlying connection. They could look at TCP header fields, such as the sequence numbers and the acknowledgement numbers, and use this to fully split and reconstruct the original connection. They could also use this information to infer properties of the subpath, like the RTTs or the loss rates, and then use this to implement different retransmission or congestion control mechanisms based on the particulars of that subpath. So now this host can send a packet to the proxy, and the proxy will immediately acknowledge the packet, ensuring that it will be reliably delivered. The proxy will buffer the packet, and then ensure that it's been reliably received by the host on the left before it deletes it from the buffer. So this is an example of how connection splitting can help TCP connections. But TCP was never intended to be used this way. It was never intended to be used in the middle of the path, and definitely not without the consent or knowledge of the hosts that are supposed to be implementing TCP. This has resulted in protocol ossification. It's hard to change or upgrade these protocols without massively overhauling the system or relying on these assumptions that these middle boxes are making. And one example of a popular proposal that has had to deal with ossification is multipath TCP. As modern networks have multiple paths for data to get to its destination, this proposal was only able to be implemented using hacks. The solution that protocol designers came up with was simply to encrypt everything, which is what we call paranoid. The most popular example of a paranoid transfer protocol is QUIC, developed at Google. So what they do is they take a lot of the same information that's conveyed in TCP and its security and reliability guarantees, and then encrypts them inside of its payload. So now that all this information is hidden, even the TCP proxies from before can no longer help. And it's been shown that QUIC is sometimes outperformed by TCP connections with proxies. Now, proxies might still be useful in some ways with paranoid transfer protocols, but only in ridiculous ways that would never be accepted by these middle boxes or the end hosts that are using these new protocols. For example, one dumb straw man is simply to credential the middle box so that they have access to all the fields inside of your paranoid transfer protocol. And this defeats all the privacy and ossification guarantees we were trying to provide in the first place. This leads to our final question. How do we enable in-network performance enhancements for paranoid transfer protocols and without ossification? How do we get the best of both worlds? We believe this is possible by creating a second protocol, which we call a sidecar protocol, that leaves the original protocol completely unchanged on the wire and doesn't rely on any protocol-specific fields inside of the packets. The sidecar will send just a small amount of additional information, but will be able to provide many of the same performance enhancements as before. Our sidecar protocols are based on a new primitive that we call a quack. A quack is similar to a cumulative ACK or selective ACK in that it communicates exactly which packets the sidecar has received. The sidecars can then use this information to implement, for example, different retransmission or congestion control mechanisms on each subpath. And definition of sidecar protocols is quite generic. Anyone can quack to anyone else or not quack at all, as long as the underlying transfer protocol remains unchanged. Here we'll discuss one example of a sidecar protocol that uses a quack. In this example, both the client quacks to the proxy and then separately the proxy quacks to the server. Using this information, the sidecars can infer information about the subpath, like the RTT of the link or the loss rate, and then implement their custom congestion control mechanisms. So for example, the proxy sidecar can simply empty a buffer of its received packet at a slower or faster rate without changing the underlying connection. while the server sidecar, which is an end host, can actually change parameters inside of the underlying connection, like a congestion window. And this is just one example. But what is in a quack? The first challenge in creating a quack is that without these TCP sequence numbers, there's no language to refer to the packets in the underlying transport protocol. We can no longer say we just received packet 1 or packet 2 or packet 3. So instead, we refer to packets by another identifier. For example, in Quick, we can use the first 32 bits of randomly encrypted data, or in general, we can just take a 32-bit hash of the packet that was received. Now, the second challenge with designing a quack is how to concisely and efficiently refer to a collection of identifiers. So with sequence numbers, I could say, I received up to packet 10, and that includes everything before 10. But now that these identifiers are random looking, this becomes a harder problem. So on the left, our first straw man is if the sender of the packets simply keeps a buffer of all the packets that it's sent, and then the receiver echoes back the identifier of every packet it's received, the sender can just take a difference between what it's sent and what it's received to determine what's missing. But this solution is not concise. It sends a lot of bytes. Now, our second straw man is to have the sender, again, keep a buffer, but the receiver, instead of sending all the identifiers, sends a hash of all the identifiers together. And then what the sender can do is identify subsets of packets within its buffer, hash those, and then keep doing that until it finds a hash that matches. And that is obviously inefficient. And the numbers on this slide refer to parameters that we set based on our congestion control division setting, in which we're quacking once every RTT, approximately 60 milliseconds. And this leads to a bandwidth delay product of around 1,000 packets sent per RTT. And you may have noticed that our identifiers use a finite number of bits, so there is a chance of collisions, but we just emphasize that in this setting, for example, having a bandwidth delay product of 1,000 packets, this chance of collisions is very small. And it's not necessarily fatal because if the sidecar protocol doesn't depend on knowing the exact set of packets. Now, we came up with a solution for a quack that is both concise and efficient. The idea behind our quack is we're solving a system of equations using Powerson polynomials, where the solutions to those equations are exactly the missing packets. This leverages related theoretical work in error correcting codes and straggler identification in networks. So the size of our quack now is 82 bytes as opposed to 4,000 bytes from before. And decoding a quack, which is finding the missing packets, is only 61 microseconds as opposed to an entire millennium. Now, this slide goes over the math behind the quack about the Powerson polynomials, and I won't go into it in detail. I'll just talk about the intuition behind the math. And the reason that our quack is small and decoding the quack is efficient is because all these operations are proportional to the number of missing packets, as opposed to the total number of received packets or the total number of sent packets. This math is really cool and highly encourage you to look into it more in our paper. Now, as I said before, sidecar protocols are very generic, and quacks can also be used in many more sidecar protocols. The only thing that we change between these sidecar protocols is who quacks to whom. So maybe only one host needs to participate in the quacking, maybe neither host needs to participate at all. We can also change what the sender does with the information in the quack. Is it a congestion control mechanism or retransmission mechanism? And finally, we can change parameters in the quack itself. So how often we're quacking, how large you want the identifiers to be, what you want the threshold to be. So in summary, in this talk, I presented this abstract idea of sidecar protocols and a functional separation between routing responsibilities and performance enhancement responsibilities middle boxes. I also presented quacks, just one way to make sidecar protocols practical by concisely and efficiently referring to encrypted packets. We think there's still many questions to be answered about making sidecar protocols practical or designing paranoid transfer protocols in the future. Maybe a quack can include health bits. Where can we deploy the quack? Is it in the browser? Is it in the middle box? Is it an access point? But in general, we think the future is bright. We're having middle boxes help endpoints improve their connections, and while preserving the end-to-end principle that our transfer protocols were designed with in the first place. Questions?
Very cool work. Thanks so much. Just one quick question: the sidecar thing. How are you going to send this on the same UDP IP port address and port number here, or is this going to be sent and identified differently, just in terms of routing differentiation based on whatever you might be having?
Right. I think it still needs to be designed how exactly, like where exactly clocks are sent. Like, do you want to open a separate connection over UDP, or maybe you can kind of piggyback it on top of like the connection that's already existing. Okay. Yeah, that's an open question for how we're actually integrating clocks.
Would you then need to actively discover these intermediaries, or would they just be sitting there and benefit from whatever comes along?
Can you repeat that first part?
Would you need to explicitly discover intermediaries, or would they just benefit from whatever flies by?
Yeah, I think there's a question about whether this is like a transparent or non-transparent mechanism. Like, do you need to know whether the intermediaries exist? I think there could be benefits for knowing it exists, because then you can maybe collaborate. But also, I think if you just like quack out into the wild, yeah, anyone can benefit just by like kind of taking that information, inferring it, and using it how they want.
Okay, cool. Thanks.
So yeah, I'm Henry Burghley from Princeton University. I had a question about layering. You mentioned the formation of TCP IP, and that is quite famously a layer built on top of Ethernet networks, where there's a set of properties provided by Ethernet, then there's a set of properties provided by TCP IP. When you first introduced the problem, it seems to me a little bit like this is a traditional layering problem, where you're trying to impose a reliability property and different properties of these different connections. And so I wanted to know your thoughts on this sort of quacking approach, where you're sort of, it's a little bit of a flatter model versus simply saying QUIC should operate at a layer above some type of link-to-link transport protocol, a little like Ethernet is below IP, Ethernet does within the network, and then you bridge Ethernet networks.
Can you clarify the question? The question is about where QUAC should sit in this layering.
No, what are the advantages of quacking instead of just putting QUIC into another layer?
The advantages of quacking instead of putting QUIC into another layer. Well, I guess just like, I might not be fully understanding your question, but yeah, I think QUAC could just sit on like UDP, or like it's not on the same layer as QUIC. I mean, it is on the same layer as QUIC, but it's not like replacing UDP. Not
replacing, but like, so like the middle box, if you have that, you were talking about transparent TCP proxy,
yeah,
and how that kind of causes problems with what TCP is trying to do.
Yeah.
What if we just formalized those proxies and had QUIC have multiple transport protocols underneath it that could all bridge to one network and then to another?
I think what we want is a way to like be able to deploy things in a decentralized fashion. So we don't want to have middle boxes kind of agreeing with these end hosts about like what layer things should be at. And I think the way that we propose QUACs is in a way that it can kind of just work with what we have now. Not everyone has to do it at the same time. I might not be fully understanding your question. We can talk about later.
Yeah, why don't we talk offline? Thank you, though.
Brent Stevens, University of Utah. I personally think that per flow fairness is a bad policy, and I'm very interested if you've thought about how QUAC interacts with aggregates of flows. Is this a thing where seems to me like I could use it to possibly control the rate? Say I have one sender sending twice as many flows as another. I could still sort of prefer to sort of QUAC inside my network and try to make sure that these are converging to different rates. Is this something you've thought about? So could you talk more about it?
Yeah, I guess it's an interesting question to think about how two adjacent hops in a path can use QUAC differently, whether they're like in the middle of the path and dealing with like many more flows from different parties with different interests, versus like if the QUAC is deployed at an access point and is like kind of managing an organization and like how those paths interact with each other and when there's more like collaboration. Yeah, I haven't thought extensively about it, but I think that's definitely an interesting. Yeah.
Hi, Frank Grassley, running CMVMware.
So something that I like about this is that you're kind of taking a design which was previously basically a layering violation and an architectural violation, and saying, okay, this can be a thing. This is a legitimate part of the architecture with protocol and kind of purpose. Do you see it that way also? And if so, does that open up new opportunities for basically more mailboxes in certain locations for other uses, or expanding the use of it beyond how it's used today?
Right, I think there's a question we can ask about are middle boxes helping us or hurting us more in our current state? And I think one number I didn't mention is that like 25% of our paths currently use middle boxes. So I think hopefully with solutions like this, we can bring it more towards middle boxes are like exclusively helping us as opposed to like also hurting us. So hopefully, yes, having this functional separation can like increase the use of middle boxes in a way that everyone benefits.
Right, let's thank our speaker once more. Our last talk in the session is going to be remote. There are two of the authors who will be available to answer your questions later. So it's Zhixiang Wang, who is a PhD student from Southeast University in China, and his research interests are in internet architecture and network security. And also Zhou Liu, who is a doctoral supervisor at Tsinghua University. He got his PhD from UAUC. He has worked on Google's network infrastructure and global networking teams. And his research interests are in data-centric systems and apps. And both of them try to build next generation infrastructures. So we're ready to see them on.
Hello, everyone. It's an honor to be here to present our recent work, DIP, Unifying Network Layer Innovations Using Shared L3 Core Functions. The Internet architecture with IP narrow-vest design has achieved great success. It shares the diversity of heterogeneous underlying technologies and supported the thriving top-level ecosystem. However, innovations about the Internet infrastructure itself are difficult. The reason could be attributed to the inability of the fixed Internet architecture to accommodate innovations in core mechanisms, such as the inability to dynamically deploy a no-IP addressing model better suited to the mobile scenarios. As a result, many Internet improvement mechanisms are ad hoc in nature. Besides various patching through middle boxes or traffic indirections. In response to these problems, our community proposed a line of research in architecture, customization, and consistency to eliminate the deadlock of innovation by increasing the diversity of Internet functions. Pioneers have contributed a lot of valuable experiences and achievements. For example, the well-known Active Network. Active Network sparked various subsequent work on network programmability, such as OpenFlow, SDN, P4, and runtime program device. In addition to Active Network, the community also proposed different Internet architectures to advocate different Internet designs. For instance, Xia and Sen. Besides these new Internet architecture proposals, a series of security-oriented protocols also proposed to change the L3 protocols, such as Netface, MiddlePlace, OPT, Epic, and so on. We have innovated so many L3 protocols. Today, we argue that unifying the key merits of these prior protocols is at least equally important as innovating another new L3 protocol. To unify these prior protocols, Todorowsky proposed the L3.5 and attempts to move the service model of the Internet from the part-defined L3 to configurable L3.5. This is an intuitive scheme for different network protocols to interact. Yet, the unification discussed in our work differs from the Torah scheme. On the one hand, we focus on researching a novel primitive to natively implement a wide range of different L3 protocols. On the other hand, because of the fine-grained primitive, the primitive unification in our work can merge different L3 protocols. Therefore, we can drive more advanced L3 protocol with various of these prior protocols. To this end, we abstract a new L3 function called primitive, named field operation. Each field operation consists of two elements, a target field and an operation to be applied on the corresponding target field. In particular, a target field is a sequence of consecutive bits present in the packet handler, with specific meaning. The operation is a functional model that takes the field as input and performs part-defined calculations or matches. For example, in the IP packet, the destination address can be seen as a target field, and the operation is 32 or 128 longest prefix match. In the NDN packet, the content name also can be seen as a target field, and the operation is forwarding information base match or pending interest table match. The PBF in OPT and the XID in SHA, and so on, can all be represented by field operations. With this primitive, we propose a new draft of the packet handler, as shown in the slide. The packet handler includes three parts: the basic handler, as shown in green, the field operation definitions, as shown in blue, and the field operation locations, as shown in orange. Then, we propose the dynamic network protocol. Here, we use an instance to illustrate the DIP packet process logic. First, after a host is connected to an accessed AS, it uses the bootstrapping mechanism similar to DHCP to get the set of available field operations. Second, the host is to formulate appropriate field operations in the packet handler, considering both the required network service and the supported field operations. Then, host sends the packets with this custom packet handler. Upon router receives the packet, it will first press the basic DIP handler to get the number of field operations and the length of field operation locations. Then, the router will press the field operation definitions and extract the field operation locations. After that, the router will operate the target fields according to the field operation definitions. We implement a prototype DIP with the commanded barefoot to final programmable switch and realize 5 different protocols with 11 field operations. We also evaluate our DIP prototype, and the result showed that DIP is efficient with the program switch. The following are some discussions and the future work. First, we recommend the ASs should agree upon an operation standard for enabling new field operation. One deployable mechanism to globally propagate supported field operations among ASs is relying on BGP communities. Second, as the field operation heterogeneous configuration in the network to be present, the inbound router may receive a DIP packet carrying a field operation that the AS has not supported yet. Here, we consider two scenarios. First, as the field operation requires all on-pass ASs to particulate. The router should return a field operation unsupported message to notify the source through a mechanism similar to SCMP. Otherwise, the router can simply ignore this field operation. Third, we do not claim that the field operation is the only option. Our community previously discussed a conceptual similar L3 function call in the context of enabling flexible L3 forwarding, such as capsule and network pointers. Yet, the field operation follows the recent research trend of runtime programmable network. For the following work, we will develop two aspects. The first is to implement a cross-AS field operation coordination mechanism to add new field operation and support field operation heterogeneous configuration. The second is to realize more network protocols with field operation. That's all. Thanks for your listening.
Any questions? Is the author, can you hear us? Are you available for answering questions?
Yes, I can.
Okay, great. So I have a quick question. So normally when an ISP deploys a new network layer protocol like NDN, they do it because it makes business sense for them. You know, they will make some money, their users are interested in it. But you're proposing to expose to end users these primitives, these operations that will allow them to construct arbitrary protocols. Now, what is the incentive for an ISP to expose that? Like, why enable end users to construct their own network layer, you know, protocol combinations, if it's not clear that that's of interest to the ISP business? Did my question make sense?
Well, sorry, I didn't catch all of that. May I have your pardon?
Should I repeat?
Yes.
Okay. I'm saying that an ISP normally it deploys a new network layer protocol when that makes business sense for them. They know how to make money off that. But you're proposing that ISPs expose to end users these primitives that will enable end users to construct essentially their own network layer protocol combinations. And I'm wondering, what is the incentive for ISPs to do that? Have you thought about this at all?
Yes. Well, I think the DIP is beneficial for both network providers and users. Well, on one hand, users are allotted to construct their desired network protocols. On the other hand, the network providers cannot support the new device by only upgrading field operations instead of replaces the underlying hardware. Further, the flexibility of field operations also enables the providers to offer different services to different users according to their subscription models. Other opportunities of DIP include implying standards, guidelines service, and official network in telemetry.
Okay, thanks. So let's thank the speaker once more. And all our speakers should come up forward. Who will start? Go ahead.
Yeah, hi, this is Wei Tao from Rise. I have a question regarding the browser proxy. It seems like you assume like if I change my policy, the network or internet is not will not changed by one user. But what if like more and more users keep using that proxy? The network status or internet status may be changed by the contribution from all the users. So in that case, different users may have different policies, and some users may have very bad performance, while others have more than average performance.
I think there was a question in the Slack channel that was a bit similar, but that's good. The observation is actually, so there's different aspects going on here. So one is in a multipath system, life should strictly get better, right? Because you have typically have the same path today's single path internet is using, plus you're getting, with today's topologies, you may have dozens of additional paths available. So then you need to be careful that oscillations don't cause problems, but that's a well understood problem that we know how to solve. So essentially life should get much better. Another point is the proxy is per user, that's just locally, it's just to implement as a easy way to implement and add it to the browser today. But if you have a closer integration, it wouldn't be necessarily a proxy. The browser would essentially obtain all the path options without needing this proxy system. Similarly, at the destination with the web server, also right now it's a proxy because updating all the web servers overnight is very challenging. Right? So this simply enables anyone with any web server to benefit from next generation internet and enabling these kind of connections. Does that answer?
Yeah, I see. Yeah, my little concern is that if you let user to specify their own policy, well, the average policy become more and more aggressive because user won't have better performance for that. Their policy is more aggressive. Everybody should follow up.
Right. Well, that's already to a certain extent happening today, right? Browsers open 10 different TCP connections.
Yes, that's true.
Right? So in this case, this enables just additional properties. So for instance, like the CO2, reducing carbon footprint, then will get the traffic to go across paths that are possibly quite different from a latency optimizing user or from a bandwidth optimizing user, or a user that says, look, I only want to use or preferentially use ISPs that have a good governance model or reduce income inequality or whatnot, right? They're actually expecting that traffic would be a lot more spread if people care for these things.
That's it. Thank you.
Hey, I'm Chijo from Cornell. I'm very interested in fault localization, and I understand the current scenario is somehow no chicken, no egg. But still, from the end user perspective, I wonder what egg I can get. Let's say if I can know where the fault is from. For example, from the Zoom user perspective, if the network is down, what else I can do? I just wait until my internet is back up. So
yeah, that's a good question. I didn't get the chicken egg part, but I got it. I think if the problem is on the user's, say, network or Wi-Fi, at least they know what it is. The other people on the session know what it is. That person has to try to fix it. However, a lot of the times the problem is not on that person's Wi-Fi. And I think that at those stages, if you look at the amount of effort and time it takes for administrators and everyone else to go diagnose the problem, it's quite a long period of time because it's cross-domain, it's cross-layer, it's all across. So I think that this would help with much quicker recovery because the amount of time it takes to even understand what's going on is lower. So today it would require either some sort of widespread tracing framework, which doesn't cover all of the components, or it would, somebody starts complaining, maybe they start looking at online forums and then they're digging through big log files.
Hey, my name is Elijah Princeton University. So in 3 of the 4 talks, we actually, it was more about giving users more information or more control, which is great. I was just like, I'm not sure about the security aspect of that. So I was wondering, for example, for Harry, like, if as a user, I could have a better understanding of what's the easiest to break on a system, then I might use it as well. And worse, I might even like use a fuzzer to find this, like the weakest link, right? And for Andrew, I'm like, wouldn't that allow a crossfire attack? I understand that, like, you know, security, using obscurity is not a good idea. I understand that, fine. But I was wondering, are we actually making it easier for attackers by giving more control to the applications and the users?
Yeah, I defer to the security expert.
Well, security is complicated.
Security is complicated.
Right, there's so many aspects. Definitely privacy issues. If we mentioned Crossfire specifically, there's a different arsenal of methods to prevent that. So in design, we actually, and this is very dangerous thing to say in this community, that we actually, because it needs a lot of explaining exactly what is meant, but we can actually achieve guaranteed properties on each path, no matter how large the attacker is, assuming the entities ASs on the path are met. And for every path, you actually get a worst case guarantee, no matter if there's a core mail attack or a crossfire attack. But that's for that part. But I think the question went in the direction, the more information you give the users, the more information also the adversary gets. And DDoS attacks, I think that can be an issue, but also if the defender benefits disproportionately, then overall we've gained something. And I would think with some additional mechanisms that we haven't discussed today, this can be actually
I do agree that there's a potential of, at least in the proposal that we're making. However, at least for those users, it's as if the system's broken. So it's not, if you want to recover and get going, I think there has to be some provision of information. So I think that at least what we're proposing is something that is quite succinct. And, you know, it is a balance between whether you want the system to be usable or secure. Best way to make a system secure is make it unusable.
For fertilization, sorry. So I have this question maybe since 15 years, maybe the time to ask it. I have the subjective impression that over the years, bandwidth improved a lot, but the rates of faults is, my subjective impression is always the same. My perceived impression. And this maybe could be due to the fact that there are a lot of things that are done by humans. So the human factors make that there are errors that occur. And I liked a lot the idea of adding a fault localization primitive. But then if there are still humans involved in this process, then maybe we still have a problem and we still have faults. I don't know if you share the subjective impression that faults are still the same. The rate of faults in internet systems is still the same.
Is it okay if I ask something about the security question before you part into this? Yeah, so thinking about quacks and its relationship to security and privacy, quacks are in response to privacy concern about transfer protocols and the information that they're exposing. So quacks will kind of make it more practical for transfer protocols to be private, but while volunteering some of the same information as before. So we can kind of be thinking about how to gain more information about the network, but maybe in a voluntary manner. Gavin.
I don't know the rate. I mean, rate depends on by what's the denominator. If it's by line of code or is it by kind of what it is.
Yeah, so the subjective. This is where I don't have coverage, for example. I have a better bandwidth when I use my mobile. But then, yeah.
I mean, I think that one thing that has clearly changed is over the last 20 years, the increasing dependence of everything we do on network infrastructure and distributed applications has made it so that the cost of downtime for individual users, people are far more sensitive to it.
Really powerful mechanism for achieving reliability in that multipath. So multipath is really magic. Having over path that's already there, a functional where you don't need to build a mechanism. Really, really powerful. So that's something we can utilize many times.
I would agree. I mean, although I think a lot of the faults are about the network. There are components inside distributed applications and RPC layers, or so I think it's important for us to be thinking much more cross-layer than. It doesn't say multipath is wrong. I think every layer should do its best, but I think a lot of the issues happen at interfaces between components, whether it be across layers or across the network.
So I have a question, another question about like kind of a follow-up question about incentives. So you mentioned that the incentive for like participating components is that you'll be able to perform a quicker recovery, right? But that's like a general incentive about like code localization. It's not really, I don't think it's an incentive in the sense about like revealing information about where the fault is occurring in which component to the end user. It's like, that's like essentially accountability, right? So is accountability really an incentive for an entity to participate in this?
Yeah, I think so. I think that, remember that across domain boundaries, the thing that if you've got two domains and you make RPC calls into something in another domain, the way these help bits would get set would not just be a component revealing its own help bits, but also if it doesn't get a response from the other domain, it would set its bits to be something is amiss. And so that would drive up. So we don't specify a whole lot about how this is done because we have to implement a prototype, or we're implementing it, we're going to try it out. But I do think keeping your peers accountable is a part of this. Now you might say, what if people lie and so on? But oftentimes we think that overall, we don't know, but I'm not as pessimistic as everybody else here about this. So I do think that being able to watch what a peer is doing in another domain, so like RPCs at a layer or whatever it is, and setting the bits saying something is amiss here would be a part of the story.
And does your system work if like all the entities in the path are participating?
Yeah, there is a story. So first of all, the system's not been built; it's being prototyped right now. So it's a proposal. But there are lots of discussions about how we would do incremental deployment, because obviously we would need a story for that.
I have a question for Hari. So what exactly is a health bit? Because quacks, for example, they're like a fact. Like these are the packets I received. Are health bits and the other information that you guys are volunteering in your networks, are those subjective?
Yeah, it's totally like up to you. It's a little bit like analogous to explicit congestion notification. It's a bit that says, I'm congested. It doesn't say how you compute whether you're congested. You as a router implementer could do it based on some queue length, which is what maybe TCP does. Somebody else does some more elaborate averaging. Somebody else does something else. It doesn't matter. As long as it's directionally accurate, that it is some reflection of congestion. So health bits have the same philosophy. We think that not specifying it is actually good. It allows people to keep evolving it. But as long as there is some way to say that things are getting bad or things are getting better. So it's intentionally unspecified.
I have a question that's somewhat related to you.
Asking about your own paper?
No, I'm deliberately not asking about my paper. I guess one thing that's sort of interesting about the Adrian's paper, about quacks, about even dips,
is that in some sense, you're exposing more controls or more channels to the network. And the argument for this is often you get optimality or you optimize for something else. So you get path optimality, you get better performance, you get different architecture. But at the same time, there is this problem that as application developers, I often don't want the network to optimize it. I want the network to provide a dumb pipe. So to go back to why Quick started encrypting it, they would say YouTube does not want Palo Alto networks to tell it how to work, right? So I wonder, like, we're on the wide area, we're not in the data center. Should the wide area really be making these decisions? Should we really be allowing the wide area to develop?
Well, essentially, you're giving the end application the ability to control something, whereas today you cannot have anything. There's a single path. So just watch. So we had a couple of prototypes, video conferencing with path control. Once you don't want to go back to the same pattern, it dynamically optimizes the path to take for the video channel, dynamically the one for the voice. It's amazing. The single path internet, it's just, I can't believe it. Like, why are we putting it
user that they can do it, right? So to go back to, sorry, Hari, no, I'm referring to our own paper. Now, to go back to like Hari's Zoom example, at some point, the reason my Zoom call is going to be bad is because I picked the wrong hardware that led me to a particularly bad path. So if these in some sense making the network more of an entity, right? It's not so much that, hey, as a network operator, my sole job is to minimize latency and bandwidth and get away with it. I still have the question about that.
Yeah. So for your original question, it's been shown that sometimes Quick is slower than TCP and middleboxes. And while Quick is encrypting a lot of things to try to prevent bad things like authentication or like privacy violations, I don't think they're trying to, like if they could receive something good at no cost, why wouldn't anyone do that? So I guess we just need to like consider whether like providing, like volunteering this extra information can actually hurt in some way, or if it can strictly help. And if it's like volunteering quacks, like you can opt out of having mailboxes interfere. So yeah, important to use it.
One comment I want to just push back a little bit. I do feel like my sense is that a lot of the practical issues happen not within one layer. A lot of what I fail are across layers. Like this mailbox thing is a good example. Something's sitting somewhere, it has some rate limiter or some firewall, and it's blocking some application traffic or doing something weird about it. And likewise, it seems to happen a lot more in different microservices. So it might be helpful to start thinking of generalizing some of these multipath-like ideas to be more than just how do we route around, how do we get out of the transport. And I agree on the concept. I do think that redundancy is ultimately the best way to do it. But I think it'd be helpful for us to think about it, not just at transport with multipath or routing with multipath, but also about whether there's an architecture that can allow for this to happen at different layers as well. So as overlays, for example, that would allow for a way to route around issues, but not just network issues.
Maybe just briefly about the overlay part. That's the last. But we should definitely. It's going to be an interesting lunch discussion, I guess. But the overlay, when you want to get very strong security, like talking about banks, or you really say, okay, this should not be attackable. And as soon as you start doing overlays, you lose a lot of these really high assurance properties. And that's an issue. You get probabilistic properties, which is good and helps in most cases, but for entities who say we really need very high assurance on a public internet, you need something strong.
Hi, I'm Divyanshu from UT Austin, and I have a question for Dina. So it's about the generalizability of the primitives. First, so for example, for quacks, the proxies, like you showed that they can perform ACK reduction, they can find out missing packets, but there might be other functionalities that the proxies might need to perform. For example, some header modification, adding some header fields. Is that something that Quacks can support, or something like Quacks can support? And similarly for the fault localization health bits, the way you mentioned is that they are not tightly specified. But if an application wants to get something more than just whether a node failed or what failed, if they want to get some more information, for example, the tracing modules that we use these days give a lot more information about latencies and such. If we do that, then does that make health bits also application specific if the application has to like fine tune those health bits for itself?
Yeah, so changing the header fields or modifying them in some ways is exactly the thing we want to avoid. A lot of the times when these middle boxes are like modifying these header fields or using them to interpret information, it's kind of to get the side effect of what you can like infer from these header fields. So for example, like combining these sequence and acknowledgement numbers, what you want is like the information you can get from it. So yeah, we don't want these middle boxes to be changing the underlying connection. That's exactly what we're trying to avoid.
Yeah, I think in our case, we do think that things like tracing frameworks or other things, the way in which health bits get set would be application specific. The system doesn't determine how they're set. The only thing we believe is that we don't want to expand that interface. We want a very narrow interface of a tiny number of health bits. So if some tracing framework has some latency numbers and wants to stick it onto the interface to propagate for WTF, we would reject that. So in that sense, there is a very strong similarity to proposals. But I think her proposal is, or their proposal is all about accounting. It's counting, it's completely off the data path. Ours is not off the data path. But the commonality is that the interface is extremely narrow.
Thank you all. Those were it was a great session, including my favorite. I wanted to ask you about putting functionality in the browser. I see the appeal, but very few people, if you're trying to, like, I've had students put stuff in Linux, to get something in Linux, you have to persuade, somebody who lives in France to do it, and then they send it to someone who lives in Germany to do it. Eventually it goes to one Finnish guy, and, I've had students get stuff in Linux. I've had students get stuff in Debian. I don't think I've had a student successfully get anything in Chrome. I think some of us here have sent students to Google for the summer to get stuff in Chrome, and the result was not. Stuff didn't get in Chrome. It was like a whole summer. It feels like if our world requires that we have to persuade these evil or unprofitable companies, depending on which browser you're talking about, to put our code in there and support it in this sort of 30 million line of code monolithic code base, that's really sad / hopeless. But you seem to have a different view, and I'd love to hear it.
Right. So obviously, if the operating system has the magic, then we only need to figure out how to convey the user's preferences now to the operating system. But the browser is a way to get it deployed, because getting code in the operating system is even harder. Right? So for browsers.
No, I don't agree with that, Adrian. I've gotten code, it's nice. But I mean, you are the most successful person in this entire room in deploying new internet architecture. No one is more successful than you. And you didn't actually get it in Brave, right?
I mean, we're right now working with it.
Yeah, okay.
So,
it seems incredibly hard.
So the point also is, I'm not saying, I just believe that through this extension, and if, of course, it gets shipped with it, right, then you can enable a lot of individuals simultaneously. It's just a nice way, and personally, I do think it's harder to get into the operating system based on the experiences so far.
When can things be written as browser extensions, and when do they have to be deployed in the browser? Because it would be simple to write like a Chrome extension, right? You don't need to have Chrome.
It is a Chrome extension. But I'm not saying this is the only only way. You just say, no, it will be opportunistic. If your application wants to use it, it's great. And if it gets built in the operating system, great. We just have to also figure out, the point of the paper also was, there's some aspects that are across layer and all the way back to the user. So this tight integration was actually useful in this case, because the user is very close, obviously. To that point. I don't know, point I forgot it, so why don't you?
So, I mean, on this thing, I mean, my sense is that most real people use apps. I mean, the amount of browser stuff is far less important than perhaps the people in this room in our community. I mean, I thought most people interact with apps, not browsers.
Okay, but look.
So in terms of deployment, maybe that's a path that
I'm not saying one or the other. You know, we're very open to hopefully apps and also use it. But if the browser apps, obviously, if the browser then has built in, the app automatically benefits. Now, remember what the point I wanted to make is we measured that with different paths. If you have a low latency path and you just do some very simple properties, like send small packets on low latency paths and larger packets on high bandwidth paths, you can get benefits of 10 to 20% faster page loads. That's actually, that provides also an incentive for browsers to build it in, right? If your web pages show up quicker, obviously this will be a benefit so that property can get deployed.
All right. I have a question for Hari. Hari, it's, you run a very large and successful software distributed systems company, and I know people in the industry, and it seems like you ask for this observability. You say, oh, I'd love to have this health bit and this health bit because I'd like to diagnose when something is wrong. Why? Like, I see these problems and I want to know why, so I'd love all this observability. And sometimes what people say is that getting you the explanation of where's the fault is more difficult than just fixing it. It's somewhere between 80% and 180% of the work of just having it not happen. I mean, what is your experience in the industry? Like, are you able to build this kind of observability, or do people just say like, no, it's actually harder than just fixing it?
Yeah, I think that I agree that today largely that's true, but I think it's not because fixing it is easier. It's because the way we're doing observability is too verbose. It's not brought to, like, there's no abstraction for doing it a little bit telescopically, which is start with something that gets to where the problem is, then start diagnosing it. So today, the basic way observability is done is developers log everything. When then people run the operation, set some log level and something happens. There's terabytes of data. So naturally, it's easier to go fix it. Well, I don't think that's because it's hard. I'm sorry, that's because the way we're trying to observe today is just way too much information.
Hi everyone, I'm Sudarshan from MIT. I have a question regarding fault localization. So do you think in future, like your health bits could become like a new, say, ECN signal or condition signal for, say, load balancing? Maybe services in between can use this for better load balancing or giving more resources to, say, users with better health bits. Or do you think it would be unfair for services to use those information?
Yeah, that's an interesting idea. At least the way we've envisioned, I don't know about the rest of my colleagues, they might have a different answer, but the way I was envisioning it was it would be used on the data path for making kind of these types of decisions, more for diagnosis and localization, and just one problem and try to solve it. I do think that would be proposed.
Michael Weiss, University of Oslo. I have a question/comment for Adrian. I would like to follow on to the point that Keith just made. There has long been a wish to give applications a richer interface to be able to express their needs to the network. I've spent too many years of my life trying to get this in place, and now we have this standard. And I'm very happy that the science community seems to like that. And I saw that you cited this transport services architecture that we have in the IETF. But it does raise a layering question. So, I mean, I also agree with the skepticism of even getting code into a browser. But if I think of how standardization works, we are getting this API, which is supposed to be a new API to the transport layer. Yet inside browsers, people are going to do whatever they want. There is also this group of web transport in the IETF, where they specifically don't care and just have a different API, and they tie it down to the protocol and choose the protocol with the parameters, because in the browser, the company likes to do it exactly in the way they want to do it, which I think is in line with what Keith said in terms of code as well and standards, right? I think in terms of layering, I would believe it's better for that to go down from the application towards a layer that's below. This is also how Apple is implementing tabs. So not a reason to put it in the US, I guess.
And also with happy eyeballs as well.
Exactly, for example.
So, but I think this is why it's so interesting to discuss this in comments. Is there some, some different tensions, right? If you like to move it up, you like to move it down. Advantages both ways. So the interesting question is, what data flow do you want to enable? What privacy? Also, there's many different aspects of privacy here about the user and so on. Is it to the US or globally, or to the entities on the path and so on. So looking forward to the discussions.
So my question is maybe for Hari. So, one of the
I feel like a qualifying exam today.
Well, having a lot of data is a problem, but I also find it's another problem where cross-service understanding of what the data from different services mean is also a big practical problem. So while having an abstraction between services might be useful, how do you solve that problem of different services understanding what the data from the other means and what the implication is for where the fault is happening?
That's great. This is the whole, I think one of the key things is we shouldn't try to understand it. We just want to try to understand where the problem is. And then it's a job of those components to go try to figure out where it is, what it is, by looking at further information. So what we're proposing is something that intentionally doesn't describe or specify how these bits are computed and propagated, or even what they mean across components. It's purely for localizing where it is. What flow is more about digging into that component or that neighbors of those components.
But then aren't you relying on that component knowing what the response here?
Absolutely.
Sometimes that doesn't also exist.
Yeah, but a lot of times it does work. It's not, again, to solve it 100% of the time, but to solve it enough of the time. I do think that a lot of the times, these things are maintaining the latencies. They're maintaining the number of RPC timeouts. They're maintaining, load levels and all of that. And every time that happens, they're probably even writing something into some log somewhere in some cases, or many cases. They're also writing millions of other things into the logs. So they do have this information. What we're saying is when you have a feeling that something is wrong, just pick 1 or 4 levels or 8 levels or whatever and just set those things. So that's all we're saying. Again, we're not saying it solves all of the problems. We can hypothesize it solves a good fraction of them. Not solves. It's identified in a good fraction of the cases.
Related question to this one. So let's assume everyone's truthful. And I'm not worrying about incentives or anything like that. But these things are enormous in scale. Like the one thing I learned from running something at Google scale is there's always failures, right? And so the question is, will I get anything other than a bunch of yellows, right, in the common case? So if I ask a query, I'll get back, out of the 500 services, I'll probably get 499 yellows.
Yeah.
And then what do I do?
Yeah, so this is a good one. This is something that it's not described in the paper in this paper, but there is a way to try to tie it together with specific requests. So for example, if you're in one of these microservices architectures, there's identifiers associated with requests, and you can tie it together with that and keep that information in some local place. There's also ways in which we're working on trying to track, a network router or a Wi-Fi or whatever is reporting these things all the time, how you track it down into individual requests. But I think that's a very valid point. We do think it's achievable without revealing a lot of the yellows, but trying to tie together specific requests. We can talk offline about ways to that. It's good.
if I may ask one last one. Starting from Adrian, your work is a lot about making the internet path transparent and more visible to the user. The user has choices, like controls the path at the domain level. And that's great. And on the other hand, there's this reality, like we seem to be going toward a situation where internet paths are shorter and shorter when it comes to the number of domains that are on them. And it's being said that most traffic today crosses, one ISP and then straight into some cloud. And a lot of ISPs offer direct connections into the cloud that bypass the public internet. And I'm just trying to reconcile these two. I mean, how does your vision fit into this world where we're going straight into the cloud?
So if you just have one hub or so, then it's not helpful. But if you ask the question, how many connections do not go into the cloud? And of course, if you look on a byte basis, then it is true most of the bytes are going nearby because they're movies and stream videos and so on, or video conferencing calls. But actually, if you ask the question differently and say, how many of the total connections are going further? There's also really a lot of connections going all over the place. And moreover, there's also been papers that look at the quality of the network to reach the cloud, and even the large cloud providers have identified that a large fraction of traffic doesn't get good connectivity into the cloud. On the order of 10% is not obtaining strong or an optimized connection based on the distance and so on where it should be. So this is definitely the case, and a multipath network architecture simply gives you different choices, even in those cases, and definitely for the cases where your communication is going further, which still we are communicating with a lot of remote entities as well.
So the conclusion is that we should still care. And now I think we can go have lunch and decide whether Harry passed his qualifying exam.